All right, thank you, Kira. So it's my pleasure today to introduce our speaker, Ying Jin. She's a second-year PhD student at Stanford University, working with Professor Emmanuel Candes and Dominic Rotenhausler. And she's also working with Zhuoran, Wang, and Junwei Lu, and producing a lot of awesome work. Well, she just started to get into reinforcement learning, to our big pleasure, but she has done some work previously on computational and statistical trade-offs. And before starting her PhD, she did a bachelor's in mathematics at Tsinghua University, and also a bachelor in economics as well. So she has a very diverse and strong technical background. And today she's going to be telling us about her most recent work with, I believe, Zhaoran Wang and Zhuoran Yang on pessimism for offline reinforcement learning. We're very excited to hear about that. Over to you, Yang.
Okay, thank you, Gregor. Thanks for the introduction. And hi everyone, I am Ying Jin from Stanford Statistics. Today I'm very happy to talk about our recent work. Is pessimism provably efficient for offline RL? This is a joint work with Zhuoran Yang from Princeton University and Zhaoran Wang from Northwestern University. So let's get started. At first, I will introduce some backgrounds of our work. We are working under the episodic MDB setting, and we are in the offline learning protocol, which brings about particular difficulty, which we call it epistemic uncertainty. I will elaborate it later. So the episodic MDP, I think most of the audience should be familiar with this setting. Like, we have a finite horizon, capital H, and at every step we need to do some planning. So at the state small h, we are at a state S of h, which belongs to an infinite state space, capital S. And the action space is finite, which we call capital A. So imagine there is an agent at the current state SH. He or she takes an action AH from the action space to the environment. And after taking the action, the environment gives a reward RH, which is bounded within 0 and 1. And the state will evolve to the next state is H plus 1. So the reward function is actually unknown, which maps the state and action pair to the bounded value. And the transition kernel, which the next state follows, is also unknown, which is a distribution over the state space. So in particular, we will start from the initial state S1 and take an action. And here we focus on the case that the action will follow a policy. So the policy is a group of policies at each step. For the policy pi h at each step, it is a mapping from the state space to a distribution over the action space. So actually, it is the pi h of some state sh is a distribution over the action space, and the action will be drawn from this distribution. So in the episodic MDP, the agent will start with an initial state S1, follows a policy pi1 of S1 and take the action from this policy. After that, the environment will give a reward R1, and the state will evolve to the next state, and it just take another action and get another reward and evolve to another state. This is our episodic MDP, and the process will stop after capital H steps. So in this case, a particular quantity of interest is the expected total reward. It is, we denote it by J of pi and x. It is the expected value of all the future rewards given the initial state if we follow the policy pi. So it has two arguments. The first argument is the policy we follow. It's like with different policies, we will have different rewards. And the second argument is the initial state S1 equal to small x. So start with different initial states, we may have different policies and get to different places. So the the quantity of interest here is the optimal policy, which maximizes the expected total reward given any initial value. So the pi star mathematically is the argmax of this J function. And we leave the second argument x out because actually the optimal policy is a function of the initial state. So a very well-known result in reinforcement learning is dynamic programming and Bellman equation we just included here. So actually the optimal policy pi star is greedy with respect to a group of optimal value functions, which we denote by q star. It is a group of value functions at each step. We will have this Bellman equation. So pi star at step edge is actually the action that maximizes this optimal value function. And the optimal value functions follows a dynamic programming step. So actually the optimal value function at a step edge consists of two parts. The first part is the actual reward. And the second part is the expected value of the best one can do at the next step. So in the expectation, this is what one can do best at the next step. And this is an expectation taken with respect to the next state, given the current state X and the current action A. So for simplicity, we denote it as the Bellman operator, B of H. So actually the optimal value functions follow this Bellman equation that QH star is equal to the Bellman operator applied to the next step. And then the last step, H plus 1, we set it to be 0. So this kind of dynamic programming and Bellman equation inspires the reinforcement learning with function approximation, where we generally employ a function class to approximate the optimal value functions, which might be linear functions, neural networks, or RKHS. I think our work falls into this regime. And the second element of our setting, the offline policy learning, where we need to learn from given data sets. The offline data means that it is collected a priori. We can imagine there is an offline agent. You don't know how she carry out her action. So the agent just take arbitrary action to the environment and get the reward and see the state to the next state, to the next step. So the data set consists of arbitrary trajectories. The actions at each step is taken by an offline agent following an unknown rule. This means that the agent might follow a particular behavior policy which you don't know, or it just improved her actions gradually over time, but you still don't know how she improves it. It is just collected a priori, and you don't have any control of it. And also, after it is collected, we have no further interactions with the MVP. So it is the particular aspect of the offline learning protocol. In this case, our learning objective is the performance of the learned policy. It's like we are going to learn the policy from the data set, and after that, we are going to employ the policy to the MVP. And we want to know if we employ it to the new MVP, to the true MVP, what kinds of performance it have. So we define the learning metric as the suboptimality of this learned policy pi hat. So this pi hat is an output of some offline learning algorithm. The input is a data set because we need to use the data set, and we also need a function class to approximate the value functions. So the pi hat is the learned policy, and the learning metric is the suboptimality, which is the difference of the actual performance of this policy to the actual optimal one. So it measures how good it is for our learned policy. And because we have the well-known result of dynamic programming and Bellman equation, we might do approximate dynamic programming using our data. So we call this method naive value iterations. we will see how this can be carried out and what kinds of problems it might have. So in the naive value iterations, we just use the data to approximate the dynamic programming process. So firstly, for the end of the episode, we set the function q hat at step capital H plus 1 to be 0, just the same as the dynamic programming. And after that, we go from the last to the first step, just similar to the dynamic programming. The first step is to do the estimation. Here we run a regression algorithm to approximately compute the approximate Bellman update of the next step. And the input is the estimation from the next step, the data set, and the function class to obtain an estimator q hat at this step. After that, we just greedily choose the best action. We optimize by choosing the action that maximizes this approximate value function. This is our learned policy. So in this case, we see that there are a lot of approximations. We need them to be very close to the ground truth to make it good. So we need to hope for a lot of good things to happen. For example, we need to hope for a good estimation. It's like we need the estimated value functions to be very close to the true optimal value functions. We also need good optimization. It's like the action we choose should be close to the actual good action, because what matters is the action we choose, because we need to deploy it to the MVP. So what does it mean by a good action? Actually, it's the final objective is a good actual performance. Like if we learn the pi hat from the approximate value functions, is the actual performance of it still close to the optimal one? Our general answer is no, especially when we don't have strong assumptions on the data set. So let's illustrate it with a special example. Let's consider a Gaussian bandit. Imagine that we have capital A arms, and after pulling the arm, we will receive a reward. And if we pull the arm small a, we will receive a reward distributed as a normal distribution. The mean value is R of A, and the variance is always 1. And the data set consists of several actions the agent takes and the corresponding rewards. And the data set is pre-collected. It's like the agent just pulled the arms for several times and receive some rewards, and you just see the pre-collected data set. So in the data set, we see that the arm is pulled n of A times. So if we follow the naive value iterations, we may estimate the mean value R of A by the sample mean. We take all the rewards corresponding to this arm and just average it to have an estimate of the true mean. And after that, we greedily optimize by taking the action that maximizes this sample mean. So the problem here is that if some arm is pulled very few times, or the n of A is very small, a bad arm A might just appear to be good by chance. So what does it mean by this? We might look at this distribution. So in this plot, we plot the distribution of the sample mean means of each arm. It's like the distributions are for each arm, and the blue one is the mean value, and the red one is the sample mean. We see that the sample mean is concentrated around the true value, the true mean, but like with different numbers of pools, the distribution will be more spread or more concentrated. And for the NA1 to be very large, the sample mean is very concentrated around the true mean. But when the pool times is very small here, for the last arm, the n of A is very small, and the distribution of sample mean will be very spread out. So there is still a very high chance that the sample mean here will appear to be very large, just overwhelming all the others. And we will just probably choose this one and ruin everything. So this is the intuition why the naive value iterations might fail. The reason is that if some policies are covered insufficiently by the dataset, then some bad ones might just appear to be good by chance. So here, there is very large uncertainty in our knowledge about a policy pi if the policy is insufficiently covered by dataset D. So insufficiently covered is like the data points in the dataset is just not many enough for us to get to have a very good knowledge of the value of the policy. So in a nutshell, the epistemic uncertainty spuriously correlates with the decision-making step, which is the greedy step generally. So roughly speaking, it is like this. The target is the actual value of this learned policy, but the learned policy is chosen from an approximate value function. So in this case, the j hat might be far from j just for some particular pi, but these small parts just will mislead us and ruin everything. So yeah,
Quick
so the
question.
result will be, yeah.
Related to this, like, how bad can this be? I mean, like, yes, I agree that there is some spurious correlation going on, but in the limit of large samples, if all the actions are sampled sufficiently, coverage happens, and eventually this process kind of corrects itself. And even, so I guess that's my question. Like, how big is this issue? Like, is this really a serious issue? Or is this like, yeah, we don't like this, but maybe it's not a biggie?
Sure. Yes, it's a good question. So imagine we have some arms, like capital A arms, and like some of them are pulled for many times, but just one or two of them just pull one or two times. And as long as there is one arm that is pulled very few times, the uncertainty in the sample mean will be very, very, very uncertain. So in this case, we will still have some overwhelming probability to get a misleading result for that. But like if you want the uncertainty in every arm to be small, you need to like uniformly many times for each arm, which is just the uniform coverage of all the policies. And for reinforcement learning, I think things will get more complicated because you have you have a lot of steps, and the approximation errors will accumulate along the time. Yeah, so the uniform coverage assumption will still be very strong, maybe stronger than what we desire. Yeah.
Okay.
Yeah.
So I also have a question here. So like this effect that you're describing here, well, this is very broadly discussed in offline reinforcement learning, right? Where the typical guarantees, they depend on some kind of a mismatch between the target, some measure of mismatch between the target and the behavior policy.
Yeah.
So can you explain this example in those terms easily, or is there something very subtle or like very specific about this example that you're explaining here that is really not kept by the usual kind of mismatch arguments?
Yeah, I think this is a special simple case of the mismatch. It's like because our target is some optimal policy, and maybe in the data set there is just some policies that are not covered well. So we will not have good knowledge of these policies. And I think this is kind of some mismatch of the data set and our target. Yeah.
I see. So it's like a specific example that explains that intuition that is typically captured by these mismatch terms.
Yes.
I see.
Yeah, I think eventually the bound will depend on some mismatch coefficient, but I think it's important to like say it's mismatch between which policies, because like for batch reinforcement learning there are a lot of like definitions for the concentrability coefficients. I think eventually the one obtained here is the weakest notion.
Right. Yeah, I see. I see. So here, you're saying that, well, there's going to be some policy which is like grossly mismatched by the optimal policy, and this can cause problems.
Yeah.
Or okay, yeah. So there are some subtle things here. All right.
Yes, yes.
Okay, okay, good. Yeah. Thank you.
Yeah, thanks for the question. I think in the reinforcement learning, the problem is like several-folded. First, it's like the bandit case, like the decision making and the epistemic uncertainty are correlated. And another particularly difficult thing is the long planning horizon. It's like the errors will be accumulated. And I think later we will present a result on the performance difference, which will explain these things more clearly. So let's just go on. Yeah. So because we have no further interactions with the MDP, we're just unable to reduce the uncertainty. So what kinds of things we can do? Previously, I think there are some approaches which require the uniform coverage for all the policies, so that if we choose some policy, the difference between its true the actual value and the learned value is small. But we just think that the assumptions are too strong and unrealistic. So we raise and answer this question. Is it possible to design a provably efficient algorithm for offline reinforcement learning under minimal assumptions on the dataset? So our solution is by pessimism. In a word, the idea of pessimism is to penalize large epistemic uncertainties. Let's just say, for example, I have a policy with high estimated value and high uncertainty. We will not be happy with this choice. And the best scenario is we have a policy with high estimated value and low uncertainty. And in this case, we will be quite confident about it and we'll be very happy about it. And the case in between is that we have a policy with a good estimated value, but it has low uncertainty. So by pessimism, we will still be happy about it, depending on how good it is and how low the uncertainty is. So next, I'm going to elaborate our solution, the pessimism for offline learning. I will first introduce our general framework of pessimistic value iteration for episodic MDP. And then I will illustrate why the pessimism principle helps. And finally, we will instantiate the PEVI algorithm for linear MDP, which is a concrete example. So actually, the pessimism principle generally has gained empirical success and also theoretical attention. In practice, there have been some recent work with pessimistic model-based methods and some work on pessimistic value-based methods, which has been successful in practice. And in theory, there are also some similar ideas as pessimism. For example, there is a recent work on the regularized fitted Q iterations. They restrict the policy class to be close to the behavior policy. This is a kind of pessimism, like we are not going to explore too far away policies. And also there is a recent work by Beckman et al. It illustrates the importance of pessimism, which is also an important reference of us. So in our work, our pessimistic value iteration, we provided a principled framework for pessimism in value iterations. Also, we have no restrictions on the policy class and coverage of the data sets. And finally, we also provide the optimality of pessimism in the sense of information theory, saying that pessimism might be the best we can do given an offline data. I will talk about it later after this part. So first, let's look at how the general algorithm works. We call it pessimistic value iterations in the general form. The first step is still to have some estimate. The first step estimator Q bar of H, which follows a regression algorithm by by the next step and the data set and the function class. So it is the black line. We will have an estimation for the blue line, the true Bellman update, but we just don't know the true Bellman update. So the Q bar is an approximation to that. Apart from a point estimate, we will have an uncertainty quantification, which is actually a confidence band. It is saying that the difference between the estimated value and the true Bellman update is bounded by this gamma h. So the gamma h is the bandwidth of the confidence band, and it is the simultaneous confidence band for each state and action pair. So look at this plot. The bandwidth is gamma h, and this is the red line is the confidence lower band, and the dark blue line is the confidence upper band. And after that, we will construct a pessimistic value function by subtracting the bandwidth from the estimated value. So actually, we are just taking the lower confidence band as the pessimistic value function. We want to remark that it is somewhat opposite to the optimistic principle in the online reinforcement learning. Like in the online setting, we also have something like a confidence band, and we just take the upper bound as the estimated Bellman update. But in this case, by pessimism, we take the lower bound. So here, the dark red line, the Q hat of H, is just the pessimistic value function we have. And finally, we optimize, simply taking the greedy policy, the greedy policy with respect to this pessimistic value function. So this pi hat h is the action that maximizes the pessimistic value function for this state. So generally, we have an estimate, the black line, and construct a confidence band and takes the lower bound as our pessimistic one and optimize with respect to it. So why does pessimism helps? We will look at some mathematical expressions and explain it. For the first result from our work is the boundedness of evaluation error. If we define the model evaluation error as iota h at this step, it is the difference of the actual Bellman update. Here, the Q hat is still a function approximate in the next step, and the Bellman update is the true Bellman update. So it is the evaluation error of at this step by approximating using this Q hat. By the pessimistic construction, we will have the boundedness of the model evaluation error. Because this is a confidence band, we will have that the true Bellman update is between the lower band and the upper band. So it is the true Bellman update will be within this interval with high probability. So the model evaluation error is always non-negative and bounded by 2 times the bandwidth with high probability, I mean. And another result from our work is the decomposition of suboptimality. So I'm not going to dive into details how this is proved, but this decomposition, I think, is very illustrative of the performance differences in the learned policy. So let's look at it. So the quantity is the suboptimality of any learned policy, pi hat. Here, the pi hat is viewed as fixed because we have learned it and we are going to deploy it. So the first term is the spurious correlation we have talked before. In the episodic MDP, it takes a more complicated form. It is the expectation of the model evaluation errors. Here, the model evaluation error, the function iota h also depends on the data set. And once the data set is given, we look at it as fixed. So this expectation is taken with respect to SH and AH. This is the random variable of the MDP. And the joint distribution is induced by this learned policy, pi hat. So it is actually the expected value of the model evaluation error, and the random variable is the SH and AH, which follows a joint distribution induced by the learned policy. We see that the pi hat is correlated, is dependent on the data set. And the iota h is also dependent on the data set. So they are spurious correlated. And in the long planning horizon of episodic and DP, it's just very hard to analyze it unless we assume some uniform coverage things. And the second term is intrinsic uncertainty, which is just the expected value of the model evaluation error. Here, the random variable is still the SH and the AH, because given the data set, the iota H is viewed as fixed. And the distribution is induced by the optimal policy, pi star. The pi star is the optimal policy for the true MDP. And the third part is optimization error. Here, it is the inner product of the approximated value function and the difference between the two policies. And the random variable here is the SH. It is the state. It is the state at this step, and the distribution is induced also by the optimal policy. So, what does it give us? By the pessimistic construction, as talked before, the model evaluation error will always be bounded between 0 and 2 times the bandwidth. So the spurious correlation is always non-positive, which helps us a lot, because no matter what this expectation is, what it takes inside is always non-positive. So we just have it to be smaller than 0. And after that, greedy policy ensures the third term to be always non-positive, because pi hat is greedy with respect to q hat. So in this case, the inner one is also always non-negative. So no matter what the outside distribution is, it is always non-positive. So after that, we have a very clean suboptimality bound, because the first and the third term are non-positive. We only have the second one. The second one, the iota h, is further bounded by 2 times the bandwidth. So we only have the 2 times the bandwidth, and the expectation is taken with respect to the optimal one rather than the pi hat, which is very difficult to analyze. So we highlight that it only depends on the trajectory of pi star. Here, the joint distribution is induced by the optimal policy. And by the previous analysis, we say that pessimism eliminates the spurious correlation, which we find especially difficult to cope with. Yeah. So a further question here for the algorithm to work is how to construct the uncertainty quantifier gamma h. Yeah. Okay, so next part. How can we construct it? How can we make the PEVI practical? First, a warm-up example, the IID tabular case, which is maybe the most simple one to deal with. Assume that our dataset actually consists of k IID trajectories from a behavior policy. And the policy has a concentrability coefficient, like the new edge star is the distribution of visiting the state action pair at step h if we follow the optimal policy. And the new HB is this distribution if we follow the behavior policy. So we only need the target, the optimal one, and the behavior one to have a ratio bounded by this copper star. In this case, we can choose the uncertainty quantifier to be proportional to the inverse of square root of visiting times of this state action pair. Here, the NH is how many times this state action pair XA is visited in the k trajectories at this step. So there are some logarithm terms that we omit, but the essential part is this one. So our pessimism gives this bound of suboptimality. It scales polynomially with the size of the state space, the size of the action space, and the planning horizon. And it is proportional to this quantity, which is generally sample efficient because the rate is -1/2. Yeah.
Can I ask a question about this?
Yes.
Would the same not hold for the naive algorithm?
Because for the naive algorithm, we need the concentration of all the policies. Here we only need the concentration of optimal.
Oh, I see. It's like just
Yeah.
with respect to
Yeah.
I star.
Yes. For the naive one, we just cannot eliminate the spurious uncertainties in the irrelevant ones. Yes.
Right. Wow. In other words, like if you are lucky, then your samples are coming from the optimal policy or something close to it.
Yes.
And in that case, pessimistic algorithms will have an advantage over the naive algorithm.
Yes.
What happens if you're not lucky? Are you going to talk about that?
Yeah, when it's not lucky, I think we have some negative or lower bound results showing that, like, the information about the optimal policy is just the essential information. Like, if it is not covered well, then maybe there is no better things we can do. Yeah, I will talk about it later. Yes.
Okay. Yeah.
Yeah. So let's just continue.
So wait,
yeah.
I also have a question here.
Yeah,
so this definition of concentrability coefficient, this seems very strong to me because it refers to like the state action distributions, whereas what I normally remember seeing in this literature is really just a ratio between the state probabilities.
Yes, because we need to have knowledge about the state and action, right? It's like we need to know whether the action is good given the state. So we need to have simultaneous information about,
Yeah, what I was thinking that maybe this is going to be like captured by these visitation counts anyway. Having like a large N for the optimal policy should be enough, and you don't need this extra assumption on these concentrability coefficients. And I guess like maybe another question is like, what is this concentrability coefficient really defined with respect to? Because like so far you were talking about like general data that was just coming from like any distribution, but this new HB, is this like the
it is
distribution of the stationary policy, or
it is from the behavior policy. It's like
I see.
Yeah,
a fixed behavior policy.
Yes.
And if you don't make this assumption that your data comes from a fixed behavior policy, can you derive like any meaningful bounds in this tabular case?
Sure. Actually, we have more general results, just rely on much weaker assumptions on data sets. This is just an IID tabular case for a warm-up because the uncertainty quantifier is quite straightforward.
Yeah, so I'm just really wondering that if you just stick to the special case of tabular MDPs, then is this the best bound that you can derive that has this concentrability coefficient, or is there a way of getting rid of that?
I am not sure whether we can get a sharper upper bound. I can just say that this upper bound will work in this case.
And what about Bandit?
Bandit, I think Bandit, if the arm, the number of arm, I think in Bandit we can just take a uniform bound for everyone, and the bound can depend just on the visiting times of each arm.
Yeah. Right. Oh, I see. So basically.
Yeah, because the concentration will depend on how many times you pull the arm, and you can just derive a data-dependent upper bound for each arm and just take the union bound.
All right. Yeah. Okay. All right. Yeah. We can get back to this later because I still wonder what's on the details here. But
Sure. Yeah. Okay, so let's just continue. So beyond the IID tabular case, we give a concrete example on the linear MDP. So the linear MDP, we say that an episodic MDP is a linear MDP with a known feature map phi. It is a mapping from the state action pair to a d-dimensional feature. If the transition is linear in this feature, and the expected reward is also linear in this feature, and we have some common assumption on the boundedness of these measures and features. So the implication of linear MDP is that the Bellman update will be linear, so that for any value function, the actual Bellman update will be linear in this feature, so that we can use the linear function approximation to work for this. So as an example, the algorithm, the PEVI for the linear MDP takes this form. We can estimate the value function Q bar by ridge regression to obtain a coefficient. And the uncertainty quantification can just be chosen at this form. It is proportional to the dimension d times the planning horizon h times the square root of this inner product. This is the inner product of the feature and the inverse of the augmented sample covariance. And we will construct the pessimistic value function just like this. The c is a constant plus some logarithm factor. I will not display it here, but you can find the details in our paper. And the last step is the optimize. We choose the optimal action with respect to this approximate value function. So instead of IID as talked before, we actually require much weaker assumptions. We call it compliance assumption. So from a high level, it just requires that the actual data set is sampled from like an MDP that evolves according to the MDP. The actions can be arbitrarily chosen depending on the previous history, but the MDP, or more specifically, the reward and the next step should be evolving according to the true MDP. Otherwise, we will have no knowledge about the truth. So mathematically, conditional on the state action pair at previous trajectories and all the reward and next step at previous trajectories, the next step and the current reward should follow the distribution of the true MDP. Here, this distribution is for the true MDP. Yeah. So this is actually a minimal assumption on the actions. It can allow for arbitrarily collected data. For example, if it is IID trajectories, then it is satisfied. And also, if the actions are sequentially adjusted, for example, the action might see the rewards and the states from previous trajectories, and the action is chosen according to that history, then the compliance is still satisfied. Or the actions can also be chosen adversarially. And as long as the dataset evolves according to the MDP, the compliance assumption will be satisfied. So we highlight that the assumption is quite weak. And for the upper bound, as an application, we have this result. This is another important theorem in our paper. If the dataset is compliant with the underlying MDP, then in the linear MDP case, we will have suboptimality smaller than this term. Here, the expectation is taken with respect to the trajectory induced by the optimal policy pi star. And the random variable is SH and AH. And here, the augmented sample covariance gamma H is viewed as fixed as a function of dataset. It is computed from dataset and viewed as fixed because it is a function of the learned policy. We highlight that it is a minimal assumption guarantee because we only require the compliance of the dataset. And also, it enjoys some oracle property in the sense that it only depends on how well the optimal trajectory is covered. Because here the SH and AH follows the distribution induced by the optimal policy. And this measures how well the sample covariance is with respect to the trajectory of the optimal policy. So we have no requirement on the coverage of all trajectories. Pessimism just helps us to identify the essential information. And also, we highlight that we give a data-dependent upper bound because here we have a remaining term, lambda h inverse, which is a function of a data set. So our idea is that offline data is what it is. So it is pre-collected. So if we are lucky and it is collected very well, then we can do better. But if it is not covered well for all the trajectories, pessimism just helps us to identify the essential information. And next, we will see that the essential information is the best we can do. So before proceeding to lower bounds, we will look at some special cases. The first one is a well-explored case, which is studied in literature. It is it can be approximately viewed as an assumption that all the policies are covered uniformly good. In this case, we will have a square root of 1 over k rate if it consists of IID trajectories from a behavior policy, and the minimum eigenvalue is bounded below by some constant. This actually ensures the good coverage of all the policies, and our convergence rate is consistent with the results in literature. And next one is the essentially explored case where we have good coverage of the optimal policy. Here, our algorithm still achieves the square root of 1 over k rate if the sample covariance is larger than the constant scale of the optimal policy trajectory. So this is different from the previous one that we only require the good coverage of the optimal one. So another question, because we can identify the essential information of optimal policy, a natural question is that, is the coverage of optimal one the essential information in the dataset? Is that what we can do for the best? Our general answer is yes. So the last part is our efficiency part. We will show a minimax lower bounds for the linear NDP case.
So could I have a quick question still regarding the upper bound? So like this general result that you showed, so this seems to be in the tabular case quite a bit better than what you were showing, right? Because there you had this concentrability coefficient, but if I look at your actual bound, then you really have like the expectation of this uncertainty quantifier instead. So it's not like a worst case, so it's not like a supremum over state action pairs, but rather an expectation over state action pairs, right?
I think the concentrability coefficient, because it is IID, so the visiting time will concentrate on a constant scale of the number of trajectories. So if it is IID, this condition will be satisfied with high probability. So
well, I guess I was like asking more about the tabular case and your general result, right? So if you just go back to your general results, like 2 slides before, right? So here you have like an right? Here you have an expectation over SH under pi star, right?
Yeah.
Whereas in the tabular result you were showing, you had the supremum over S and A, right? And that seems to be like a lot worse than taking the expectation, right? So if you have some terrible concentrability,
but here the expectation,
it shouldn't really bother you, right? Because you would only see that huge ratio with tiny probability in this expectation.
Yes, that's a good point.
So then this starts to look an awful lot like these usual mismatch notions in offline RL papers, where you see this kind of Rényi divergence between pi star and the behavior policy. Is this related to it at all?
I am not very sure about it, but here the random variable is SH and AH, and it follows the joint distribution. So I'm not sure whether there are some pairs, some small pairs that the optimal policy will visit for very small probability, and the mismatch does not matter so much. It may be a little subtle. I'm not sure about it. But like in our formulation, we just need the general coverage after we take the expectations.
All right. Yeah. Okay. Yeah. Well, I guess my questions here are a little bit technical. So yeah, let's get back to these later. I'll just let you go on. All right.
Sure. Yeah, we can talk about this later. Yeah. So The answer is that the coverage of the optimal trajectory is the essential information in the data set. So mathematically, we say that pessimism is nearly minimax optimal in the linear setting. So as a recap, the upper bound is like if the data set is compliant from the true MDP and we have a pessimistic policy, then the suboptimality will be bounded like this way. And here, the data set simultaneously gives the pi hat and the lambda h. And we have a lower bound like this. For any offline learning algorithm, the supremum over all the linear MDP and data set compliant with this linear MDP, the expectation of the ratio will be bounded below by a constant. If we take a closer look at this ratio, the numerator is the suboptimality of the output algorithm on the true MDP given the initial state. So this one depends on the data set. And the denominator is also dependent on the data set here. The lambda h is computed from the data set, and the expectation is taken with respect to the state action pair SH and AH. So actually this one, the denominator is a function of the data set. So both the numerator and the denominator is dependent on the data, and their ratio will be bounded below by a constant. Our point is that our suboptimality upper bound is data dependent. It depends on how well the optimal trajectory is is covered. And for the lower bound, we also have a matching ratio for the suboptimality and this essential quantity. And this reveals.
Yeah. Oh, sorry. Go ahead.
Yeah, sure. Yeah. So this reveals that our suboptimality we can achieve goes with this information quantity, which reveals how well the optimal policy is covered. And by using this lower bound, we will know the essential hardness in the data set. It just depends on how well this sample covariance covers the optimal trajectory. And if this quantity is small, let's go back a bit. If this quantity is small, then the upper bound tells us that we can do much well. And if this quantity is large, saying that the sample covariance does not cover the optimal policy very well, our lower bound will say that the suboptimality will also go with this quantity, and their ratio in expectation will be lower bounded by a constant. So our lower bound result completes the picture of our understanding of pessimism by showing that the pessimism is actually minimax optimal in the linear MDP. Yeah. So that's basically what I want to talk about today. So if we have questions, feel free to ask.
Let's first clap.
Mm-hmm.
Thank you.
Yeah, I do have a question. So maybe I jump in and start with the question.
Yeah, sure.
So it seems that what you have technically is a weighted minimax.
Yes, yes.
Right?
Yes.
And so the weighting chooses different points on the Pareto optimal frontier for this problem of offline policy optimization. Any weighting would choose a Pareto optimal point. You choose certain weighting that makes the pessimistic algorithm like it shows that the pessimistic algorithm is indeed on the Pareto front. But maybe other algorithms are also on the Pareto front.
Yes.
Maybe other points on the Pareto front.
Yeah, probably.
Yeah. So did you think about this? Like, is pessimism really that unique, or do we have a lot of different choices here? So how does this work? Full disclosure, I've been thinking about this a little bit. And the paper is going to come on archive soon. But
sure.
Yeah. So
yes.
have you thought about this?
Yeah, sure. Yes. Actually, in working on the pessimism, we are thinking about what kind of optimality it has. And by the upper bound, we find that it can identify the essential information of optimal trajectory. That if the optimal one is covered well, then it is good. And we don't need any other trajectories to be covered well.
Right.
So in deriving the lower bound, our idea is that if it is optimal, then the suboptimality should go exactly with the coverage of the optimal trajectory. And all the others are irrelevant. So we choose this formulation to take the ratio of these two things to reveal this.
I think that this is awesome. Just I was wondering about whether this is a sufficient reason to prefer pessimism.
So
basically,
maybe
the naive algorithm is also minimax optimal. Let's say with uniform weighting, right? And maybe you take some other algorithm, and then that's also going to be minimax optimal in some other weighting.
Yeah.
And whether you've been thinking about this, or like the broader question is, and as Gerke said, it's like controversial or not, but like it's really just the thinking about whether pessimism should have a unique place in our toolkit. I mean, like, regardless of the answer to that question, like knowing that pessimism is minimax optimal with respect to this base, it's a really awesome result. It's nice. But there is also this bigger lingering question of, like, is pessimism really that unique? Or do we have like a lot of different choices for these weighting functions? And then whatever you choose, you will get some algorithm, sometimes pessimism, sometimes not pessimism. What do you think?
I think if you actually replace pessimism with let's say optimism, right, and you still get an upper bound. And that upper bound, the only bad thing about that upper bound is that it depends on the data itself. And also there could be a data set that gives a smaller upper bound if you use optimism than if you use pessimism. And I think correspondingly, you can replace the lower bound in like exactly the fraction on this page. You can replace the denominator with
the corresponding term.
Probably there's the corresponding term. But I think on the entire Pareto frontier, the pessimism one is the only one that can be independent from data. So here you only have the expectation with respect to pi star. So otherwise, there could be expectation with respect to pi hat. Like the pi hat is some policy constructed based on data.
Independent of data or independent of distributions? Like this is a distribution-dependent weighting factor, right? That you have here.
This depends on the NDP itself, but it does not depend on the data.
Right. And so you're saying that for optimism, it will necessarily depend on the data itself? I mean, like, can't you just like make it distribution dependent?
I think so. Actually, we have tried if we use optimism, and then the only difference here will be the expectation of pi star on the denominator will be replaced by the greedy policy, like in that like obtained from the algorithm. And I think the
so that depends on the distribution, not really on the data, right?
Well, because that policy is constructed based on data.
Well, you could take the expectation of that, I suppose, and then it doesn't depend on the data. It only depends on the distributions involved. Maybe I'm just too picky about this data dependence, or like, but I just want to clarify: do you really like care about the data dependence? Can't we just like always get rid of data dependence by taking more expectations?
I think it's hard to say. Yeah, because the data is pre-collected. It's something like it is given to you and you don't have further interactions. And what we care about is like what information we can extract from the data that helps us to do better.
Sure.
And
so think
if wait,
wait.
Please go.
So think about a multi-arm bandit case. So our bound only depends on how many times the optimal arm is visited. And if you use other mechanism, then it will depend on how many times some other arm is visited, right? So we think like the only choice of bound that can depend on some independent quantity. The optimal arm is kind of the independent quantity that only depends on how the rewards are, not the data.
Ying Jin, did you want to say something?
Yeah, if we use optimism in the multi-arm bandit, for example, if the uncertainty of one arm is very huge, you only pull it one times, and the reward is small. The optimism gives you a very high value, and you might not want it, because by pessimism, you can allow a lot of arms to be insufficiently pulled. Like, as long as the optimal one is explored well in the data set, others just does not matter. And we will say that this is the essential information. And by optimism, we can do that. Yeah.
So what if the data set was collected by an adversary and I didn't want to pull the optimal action too many times, but I pulled the suboptimal actions a lot of times? Shouldn't I use an optimistic algorithm in that case?
I think we still need to use the pessimism, because actually our analysis can be modified to gap-dependent analysis. Yeah, and after that, it will depend on the gap plus the uncertainty. For each arm, we define the gap plus the uncertainty, and we take infimum among all the arms, so that if the suboptimality one has a small gap and the uncertainty is also small, actually our pessimism still gives a small suboptimality gap. But it is just the theoretic perspective. We can just use this algorithm and give it a better analysis, and it might give us more information that we want.
Okay. All right.
It's just, yeah.
Yeah. In the meanwhile, the chat exploded.
Thanks for the discussions.
Yeah. Okay. Thanks for the answer. So I think that we should probably discuss what's happening in the chat.
Yeah. Sure.
Gaggy, do you wanna you were not following it? I didn't look. Or Kiara, did you look at
not that much.
what was happening?
No, I was a little bit like stuck on this discussion regarding like data dependence of the bounds, because the way that I look at these bounds, these are also data dependent, right? So this gamma matrix that depends on the data, right?
Yes.
So
distribution dependent if you take the expectations. So
it actually depends.
MVP, the behavior policy. That's it. Sorry, Ying Jin, you were saying something.
Sorry, just go on. Yeah.
Good. No, I'm done.
Okay. So it is data dependent, but we highlight also the oracle property. Although it depends on the data, essentially it is only depends on how well this optimal one is covered. So let's say that if I am given the data set and all the policies are explored very well, so just naively we can do very well. But if only the optimal one is covered well, and there is something like a treasure for you to discover, but there are a lot of noises because a lot of irrelevant policies are not explored well, and there are a huge uncertainty. And then by optimism or the naive value duration, you will just be blurred by this noise. But by pessimism, you can just identify this treasure and get a much better result. This is kind of data dependent and oracle property of pessimism. It's like, as long as the good one is explored well, others just doesn't matter. But for other approaches, you might need everything to be explored well. That's we think that's a crucial difference.
Right. So I guess really the bottom line is that if you were not pessimistic, then you would also have the expectation of the same thing, but under pi hat, and that is sort of very difficult to say anything about.
Yes, exactly.
I see. Okay,
is it though?
I think I understand better. Well, yeah, I guess, this is like becoming a little bit controversial, right? So that, so without pessimism, you can get like a similar bound where you're going to have like this expectation under pi hat.
Yes.
But is it like really so difficult to control, or it's really just something that you, well, didn't want to do?
There would be some additional terms. The bound would have a different form. I would suspect that it
the
would
bound
also
itself would be
minimax
strictly larger, no?
Mm-hmm.
The bound itself would be strictly larger if you follow the same decomposition.
Yeah, and yeah, like that's the question, whether the naive algorithm is also an operator frontier or not. But I think it is. Just not for the case when the data set is collected to support pi star.
Is that like in that case there are all the arms that are explored well, so that you are doing well, or
yeah,
or like
so when, for example, you would have an example like just bandits, all the arms are explored equally often. Then that's kind of the worst case for the minimax unweighted case. And in that case, the naive algorithm is doing as well as the pessimistic one, so it's minimax optimal.
Sure.
So it's kind of like, yeah, it's like they're not. It's hard to say. I think that any of these algorithms is inherently to be preferred unless we have an extra, I don't know, extra and extrinsic kind of idea about how the data is collected. So if the data is collected with a mindset such that, well, we want to sample trajectories that pi star might be going on, and very often that's the case, right? Like, so then it's natural to use the pessimistic algorithms, right?
Yeah. Actually, our approach is general because we try to make the minimal assumption on the data collecting procedure, and like just
And in a way, that's the minimum, like, or that's something that comes naturally to assume that the data is collected so that, like, supposedly it is going to sample things that where the optimal policy would go more often than not. Even though I don't know, like, who knows how data is actually collected in whatever application. We know that in a lot of applications, data collection is just opportunistic. People collect data based on what's easy, not based on what's good or what may be good.
Yes.
Right.
Yeah, an extreme example is Thompson sampling. On the online setting, it's like we are being optimistic by using UCB. In that case, following that, if we have no restrictions on the budget, maybe we can do whatever we want, and then I think for those algorithms, the optimal arm will be poured many times, and in that case, pessimism still works because the uncertainty for the optimal arm is small, and the value it depicts is also very high. And and in that case, we will have to choose the optimal one. And a case in between is that the good ones are explored well, or the suboptimal one is explored well. But there are also some large noises, like there are some just random person you just poured once and it appears to be very good, and being optimistic might be very dangerous. But like by a little pessimism, we are still doing relatively good.
Yeah, I guess there were some questions about this in the chat. This question specifically was, whether you think that optimism or pessimism would be better after you collect data following an optimistic algorithm, and then you just answered and saying that, well, you think that pessimism would be doing better. I think that's correct.
So I have a question regarding the lower bound, because I obviously don't understand it as well as Chava does. So here I'm just trying to parse this expression here. Like, what is really D? Is it the data set or a data
it is
distribution?
a data set. It is a data set.
Because I see like a supremum over D and then an expectation with respect to D. So like, what do these things mean?
Yeah. D is the data set, and it has to be compliant with the underlying MDP. And actually, it consists of states and actions the agent take and the reward it receives. And
right,
it can be.
But then I'm confused about the expectation indexed by D. What does that mean?
Yeah, because the process of collecting data is also random, right? It follows the true MDP and start with the initial value. The agent might take any action, and after that, the process of receiving reward and the state to the next state is also random, and the process by compliance need to follow the true MDP. And
I think, Gerge, this is just technicality, but it's a shorthand. But my understanding of this compliance is that it says that you can have any history-dependent way of choosing actions by generating the data.
yes.
And that's exactly the class that you're talking about. And you're taking the supreme or all possible history-dependent data collection policies here.
Yes.
I see, right. Yeah. So basically that supreme is taken over like all data collection policies.
Yeah.
And then D is like the distribution that this can generate.
Yes.
And then you take an expectation with respect to that of this ratio, and then you show that this is lower bounded.
Yes. Yeah, you might refer to our paper for more details on the construction, but the construction is not so complicated. The data set is just composed of some predetermined actions. Yeah. So that
I see. So it's like a sequence of actions that is fixed.
Yes.
I see.
It's like
and the MDP?
The MDP, we can see that for a while. The MDP is also simple. Awesome. It's like start with a fixed initial state and jump to two rewards, and the probability of jumping to x1 by taking the action bj is pj, and the other choice is to go into another one, and this one is of constant reward 1. This one is of reward 0, and it will always stay here. So the actual thing that matters.
So that's a bandit problem, right?
Yeah. So the actual difference is the probability of jumping to x1, and we say that if the actions are predetermined, there will be a gap in between and the performance of any policy on 2 hard instances. So our construction is just a modification of the Lecam 2-point method. It's like we construct 2 instances here, like the probability of jumping to x1 is p star and the others are p, and the other is like we jump to x2 by p star, but others are the small p. So the optimal policy for the first one will take b1, but the optimal policy for M2 will take B2. So in this case, because the optimal policy is different, any policy will either make a mistake on the first one or a mistake on the second one. And using arguments like Lecam's method, we can bound the lower bound with some total variation or KL divergence like that. Yeah.
Right.
Yeah.
Yes.
Yeah.
There was a question on YouTube.
Yeah, sure.
Sapana was asking practicality of this, whether okay, I read her question. Maybe I missed some details, but isn't how well pi star is covered difficult to determine in practice? Is practicality of pessimism discussed in the paper?
Can you please repeat it for a bit? I didn't follow what's the linear?
I guess the question is this bound easy to evaluate based on data? No?
I'm not sure whether that's the question. I think that the question is, well, I wish he was here. The question is more about whether we should use this bound as a guiding principle when thinking about some practical problem. So ideally, if you have some theoretical result, then you could go and like evaluate your practical situation to see whether that result is going to apply, is going to tell you something interesting or not. So how do we think about this?
Yeah, I think for an estimation of this upper bound, maybe it's possible to have an estimation using the approximate value functions by the optimal trajectory. Like, yeah. But I didn't quite understand what kind of practical thing it's like, because we have a concrete example for this pessimism value iteration that can be applied in practice. So we think that it is just useful to be deployed.
Wouldn't the possible answer to this be that, well, the results ensure us, this minimax, weighted minimax optimality result, is that at least this algorithm is on a Pareto frontier. And if you care about this type of weighted minimax criterion, then like this is the best that you can do. Anyways, regardless of the instance. So here there is a supreme over all the instances. And you have this guarantee that holds no matter what the instance is. So in a way, like you have a robustness result that says that, well, it doesn't matter how the data was sampled, what the MDP is, your weighted minimax optimal. And then the second question is, are we really happy about being minimax optimal this way or not? But that's maybe not really a practical, I mean, like it's highly practical or like a pragmatic question of like just thinking about what these criteria means.
Yeah. I think the lower bound or the minimax lower bound is kind of understanding how hard the problem is. It's not to guide us to like how to design an algorithm. How to design an algorithm is answered by the upper bound. But the lower bound is kind of like, we are going to know what is the essential difficulty in this problem given this data set. Because like in statistical problems, the minimax results maybe tells you that you just cannot go further. You just cannot keep improving your algorithm and get further better results because there is a barrier of lower bound there. And I think our lower bound is in a similar sense, like it depends on how well the data set covers the optimal trajectory. And if it is not, then the suboptimality might be bad for any algorithm.